this will be mini lecture 17. This is kind of a transition lecture, if you will. We spend the first month and a half almost essentially learning the basic circuit analysis method using DC circuits, namely using resistive circuits, resistive and sources, independent sources. And primarily, we needed to learn mesh and nodal analysis. We also learned Thevenin and Norton model. But we need to learn mesh and nodal, which are the main circuit analysis methods that we use for solving circuits. And typically, when we solve circuit, we talk about finding current, voltage, power on elements, if you will. Okay, so we're about to transition slowly to the second main section of the course, which will be what we call transient analysis of circuits. Namely, we're going to introduce inductors and capacitors, and we're going to bring in differential equation to circuit analysis, first and second order differential. So this particular lecture is really a detour. It's a lecture we want to give students in the lower division, circuit course, an introduction to operational amplifiers. This is specifically important for students who are not electrical engineering students, because operational amplifier, abbreviated op-amps, you're going to find them in a lot of engineering applications, cars, bridges, a lot of little gizmos that use essentially op-amps to amplify signals. That's what op-amps are. They are used as a cheap way to do amplifications of signals or voltages. So because they are so prevalent in so many engineering applications, we wanted to give you a basic introduction of op-amps in Engineering 17. I am going to exclusively consider the ideal model. They are more advanced model for op-amps. We are not doing that in this course. Maybe if you take more courses in electrical engineering, you will learn those. But in this course, we're looking at the ideal model. We're doing an introduction of op-amps. I want you to do some basic analysis, essentially basic circuits of op-amps. So let's share screen with the PowerPoint. So what I'm going to do today is give you a basic introduction of op-amp, tell you how to analyze op-amps, and then we'll do a couple examples to kind of affirm that. And I think that will be a good introduction for Engineering 17 student basic circuit analysis. So I'll start by saying that many times in this circuit, I talked about this course being called linear circuit analysis, many places, many universities in this country. This is the one exception to the rule. So op-amps are electronic devices. Op-amps essentially, we're going to talk about a little bit about them, and I'll show them to you actually on Amazon so that you see that they're easy to get. Originally, they are built in the 1940s using vacuum tubes, large vacuum tubes, because most of you don't know that even televisions were using vacuum tubes not so long ago. But they were built to provide large amplification. Okay, you wanted to essentially multiply a voltage by 1,000 to amplify that voltage, then op-amps was a good way to do that. 500, 1,000 were typical gains of op-amps that you can accomplish using op-amp circuit. They're essentially a device made of transistors and an electronic device. They're an electronic device, so they're made up of transistors and resistors, and largely they're designed to provide large gain. A particular characteristic of op-amp, they have a very high input resistance and a very low output resistance. And of course, we've already mentioned the fact that they have large gains. Okay, so for my purpose in this course, I'm going to show you the symbol we use for op-amp, and then we're going to learn how to essentially analyze them using circuits, using the basic circuits we've had. So we're not seeking to have any kind of expertise on op-amp. This is a basic introduction. We're going to focus on the ideal model. So this will be the symbol we use for op-amps. You will see that op-amps are a three terminal device. We have the input terminals. One of them is called the non-inverting input, which is at the positive terminal here. We call it V2 here. And we have the inverting input, which is V1. What op-amp does essentially, it produces an amplification, which is the gain of the op-amp, an amplification between the input terminals and the output terminal. Okay, the output terminal here, I'm calling it V0, and it's an amplification between V2 and V1. Largely, you can look at op-amp as having very large gain. What's interesting about op-amp, the op-amp itself has a gain, but how you connect the op-amps in circuit is going to determine the overall gain of the circuit, the overall amplification you get from the circuit. And you're going to see that in the example that I have. The other thing I want you to know is that op-amps are basically a collection of electronic devices inside of that symbol that you have. It's not the typical resistor and sources. It's essentially electronic devices as well. So if you know anything about electronic device, if you think about your stereo system at home, it doesn't work unless you plug it in. So what does that mean to you? That means you have to power electronic devices for them to do that amplification, for them to do whatever they do. So when we talk about electronic devices, they also need to be powered up. What you're seeing here in my lead that says V plus and V minus, these are the power sources for the op-amp. In reality, the output of the op-amp is restricted to be in the range of V plus and V minus. You can't amplify unlimited amount. So you have to amplify based on the power source you've got. Okay, so what I'm saying essentially, the output of an op-amp in real life is bounded, is limited by the power sources that the op-amp has. Okay, so we're going to learn how to use that. Most time actually in my problems, I'm going to not show you the V plus and V minus lead, because again, we're looking about a basic introduction to op-amp circuit, but you will see that in many textbooks and many technical journals as well. You will see the biasing, what we call biasing voltage. So let me show you what the op-amp looks like in real life. So on the right, you're seeing the old 747 chip, and these are the description of the pins, okay? Pin 1, 5, and 8 are of no consequence. Basically, you can ignore them. They don't do much. So what we have here, essentially, we have the non-inverting input at V2, which is pin 3, the inverting input, pin 2 or V1, the output is pin 6, and then we have the biasing voltage V plus on pin 7 and V minus pin 4. Okay, so that's the op-amp, and again, the output voltage must be constrained by the biasing voltage, the range of the power supply. Okay, so that's what an op-amp looks like, and I'm just going to quickly show you the Amazon. I search on Amazon and show you that basically they're pennies. You can buy, I'm showing you this one here, you can buy essentially for $8.99, you can buy 20 of the 741. Okay, so this is fairly common, easy, because they're a cheap way to do amplification of signal. So you can find them for literally pennies on the dollar. Okay, so let's go back to the PowerPoint here. So our goal here is not to buy op-amps on Amazon. I just show you that to show you the availability, not to promote Amazon, by the way. But we want to know once we have an op-amp. So your objective here is, I'm going to put op-amp or op-amps in circuits, and I'm going to ask you to analyze these circuits. So the next few minutes, we want to learn how to do that. All right. So this is the model for the op-amp. I'm putting the model inside of the op-amp symbol, and large, obviously. What we have for the op-amp, remember I made mention that dependent sources are used to model electronic devices. That's a perfect example here. Okay. So the model for the op-amp on the input, it's a resistance we call R sub N. Okay, that's the model for the op-amp. And on the output, it's a dependent source with a value, dependent voltage source with an output A times V, V being the voltage at the input between V2 and V1, in series with R out. It wouldn't say with a resistor, R out. Okay, so that's the model for the op-amp. If in the situation that if we were not doing an ideal model, of course, in the ideal model, I'm going to assume that the input resistance is so large that it's infinite. In real life, it's large, it's not infinite. So in real life, you have a value for the input resistance, Rin. The output resistance in real life is not 0, but in our ideal model, again, we're going to only do the ideal model in this course as an introduction. We're going to assume that the output resistance is very low, and we're going to assume it's 0. Okay, what does that do for us? If the resistance on the input is infinite, that means the current into the op-amp terminal, we're going to assume it's basically small enough to be considered 0. In real life, it's a small current. Okay, so we're going to assume the current at the input terminal of the op-amp is 0. And we're going to assume on the op-amp, the model essentially has no resistance at the output, so we're having that dependent voltage source on the output. Okay, so we're going to assume, because the gain is very large, the voltage difference between V2 and V1 is very small. And we're going to assume in the ideal model, small enough, we assume they're basically of the same value. So V1 is going to be almost equal to V2. We're going to assume it's equal in our ideal model. Okay, so this is the way we're going to treat op-amps. And you're going to see when I treat op-amps, I'm going to exclusively use nodal analysis. You can see my reference node here inside of the model here. Okay, so let me recap how we're going to do the model here. We're going to do the model by saying the input resistance in the model is so large, we assume it's infinite. So it's essentially the current is 0 on both input of the op-amp because the resistance is so large. We assume that on the output, resistance is so low, we assume it's 0. So on the output, we have a dependent voltage source with the gain of the op-amp A times the voltage difference between V2 and V1. So here, pretty soon I'm going to tell you no KCL here because you have a voltage source at that node connected to ground, all right? And then because the op-amp has such a large gain, we're going to assume the voltage at the input is very low, low enough so that V2 is about equal to V1, okay? So those are the rules that we're going to use when we solve problems with the op-amps, okay? So I'm going to, again, let me just show you that in a more succinct way. So when you see an op-amp in this class in a circuit, you can assume that it's an ideal op-amp. Okay, we're not going to do anything but ideal as an introduction in this class. If you take, and by the way, the ideal op-amp is a pretty good estimate of how the op-amp perform in real life. If you take more advanced courses in electronics, you will see differently. You will see more exact and different model. So I wanted to put how we're going to treat the op-amp in our circuit. So I've created this ideal op-amp's golden rules here. So the first thing we're going to do, we're going to assume that the op-amp has an input resistance so large that the current in both input terminals is 0. In real life, the current is small. We're going to assume the two input nodes of the op-amp are at about the same value. In real life, there's a small voltage drop, but in the ideal case, we assume they are the same value. We're going to exclusively use nodal analysis to solve op-amp problems, okay? And then we're going to do no KCL at the output of any ideal op-amp, which is the only thing we're concerned in this particular course, okay? So these are what I call the golden rule for treating a circuit with an ideal op-amp in this class. We're going to apply those with our nodal analysis, and we're going to be able to solve circuit with op-amp. So I'm going to do some example to show you that, essentially. So let's look at a basic example. One, this is actually one of the most common op-amp circuit. It's essentially, it's an inverting amplifier. And the question is to calculate V0 over Vs. So assume Vs is a known value, and we're looking at the ratio of V0 over Vs. And what this circuit allows engineers to do by selecting the value or the ratio actually of the resistor R2 and R1, the ratio between them, you can actually determine how much amplification you get between V0 and Vs. Okay, so that's a nice, easy circuit to do. You can select the resistor, and the ratio will determine the value of the amplification that you get between the input voltage Vs and the output V0. Okay, so it's asking you for that so-called voltage gain of the entire circuit. The op-amp has its own gain. We're going to assume the gain of the op-amp is very large, but the circuit will have its own gain, and we're trying to calculate that. So remember so before I start solving anything here, again, I'm going to choose a reference terminal here, a reference node. And then what are we going to do here? We're going to say, okay, no KCL here. We put on X, no KCL at the output of an op-amp. That doesn't mean no current, by the way. Obviously, the op-amp puts out current. All right. No KCL here because in the model, we have a dependent voltage source at the output. No KCL here. We're going to assume the current here and the current here are both zero because the op-amp has a large resistance at the input. So we're going to assume the current above zero. And then these two nodes, we're going to assume they are at about the same value. So that's the golden rules on how we're going to use this. So in essence, I'm adding those golden rules onto nodal analysis to solve the op-amp circuit here. So let's see how that does. So we're going to exclusively pick nodal analysis when we have an op-amp problem. All right. So I chose the reference node here at the bottom, and then I label my other node. Of course, you see me doing this. I move the VS from the source to this. In essence, I'm putting my source equations here. This node is basically the source equation. So this node is VS. So I have V1 and V naught. Okay. All right. So the first thing I'm going to do, again, one of the op-amp rules, the two terminals, they're at about the same value. All right. So one of them is grounded here. One of them is the reference node. So I'm basically going to assume V1 is 0 because of the ideal op-amp model. Okay. Because V1 and V2, of course, we don't have V2, but the two terminals of the input, the two input terminals of the op-amps are at about the same value. In this case, one of the terminals is grounded. So the other terminal must be 0, must be at 0 volt as well. And then we don't do KCL at the output of an ideal op-amp. We are only concerned about an ideal op-amp in this course. So I'm going to do KCL at node V1 alone, because obviously I also have a super node here, but I'm not doing anything with the super node because it has the reference node. Okay. So I do KCL at node V1, and you can see here on this lead, there is 0 current. Okay. There is 0 current on that lead because the op-amp on both lead has 0 current. In real life, it draws a small amount of current. So I1 plus I2 equal to 0. Then I'm going to go ahead and do Ohm's law for I1. I'm going to do Ohm's law for I1. So I'm going to say I1 is Vs minus V1 divided by R1. V1 is 0, so it's Vs divided by R1. And I2 is V naught minus V1 divided by R2, and V1 is 0, so it's V naught divided by R2. So I take those two Ohm's law equations and put it in the KCL and collect terms and solve for V naught. And you get V naught is minus R2 over R1 multiplied by the input voltage Vs. This is why they call it an inverting amplifier because of the minus sign. So by essentially choosing the ratio of those two resistors of R2 over R1, we can decide how much amplification we have in this op-amp circuit. Okay, so that's a pretty nifty things to have. That's what op-amp does for us. It's a quick, honestly cheap way to achieve amplifications of signal when we need to. Okay. So I hope that makes sense. We're going to do a couple more problems just to get that going, and hopefully, and obviously you also do you'll have a homework assignment to help you practice this. But namely, what we're looking at here when we have an op-amp, let me just reemphasize, we're always going to have ideal op-amp in this course. We're not looking for anything more sophisticated than that. So when we look at an ideal op-amp, we look at no KCL at the output. In the case here, V naught is the output, no KCL here. We're looking at the two terminals input are at about the same value. This particular case, it so happened to be the ground, so they are at 0. And the current, the op-amp draws no current on its input. There is current on its output, otherwise the op-amp would be dead. Okay, so there is current on the output. All right. So, okay. So again, the gain of the circuit is minus R2 over R1. The minus sign gives it the inverting amplifier name, if you were to this circuit. Okay. All right. So let's look at a second problem here. And half-piece, I'm not going to ask you to graph things in this course. This is a pretty good, kind of a little bit of an elegant problem to solve. So this problem is asking to graph V naught versus VG. Okay. So, and graph it between VG going between 0 and 12 volt. So we have to solve this problem. Essentially, using nodal analysis. So I'm going to talk about it right now. So I'm going to have a node here. Okay, so I'm going to put my reference node right here. All right, so I have a node here. So I'm going to have obviously a super node that has both voltage sources combined because they share that common node. So this node is going to be 6 volt is going to be here. Okay, and VG is going to be here. Okay, these are my two source equations here. All right, that's how I'm preparing this circuit. All right. Okay, obviously here I have a node here as well. Okay, and these two nodes are going to be the same value because of the ideal op amp. So this node here will be 6 volt as well. Okay, since that node is 6 volt and this one is 6 volt. How's that? All right, and then I'm going to do KCL at that node and so forth, and we're going to see how that plays out. Okay, no KCL about the super node. So let's see how we do. And then no KCL at the output here of the ideal op amp. So let's see how we do this. So I wanted to give you a feel for it before we go ahead and solve that problem here. So again, you see me putting VG here. That's my source equation. And then pretty soon I'm going to say V2 is 6 volt. And V2 is 6 volts. So is V1 because of the ideal op amp. The two terminals of the input are at about the same value in the ideal model. All right. So V1 equal to V2 equals 6. All right, and then I have V3 on the output. So no KCL at V3. So where am I going to do KCL again? We have a super node here, like this. But it has a reference node, so I don't do anything about it. So that's why I don't usually draw it when it has a reference node. Okay, so I'm going to do a KCL. The only place I can do a KCL is at node V1, because no KCL at node V3. Okay, so KCL at node V1, you get I1 equal I2. All right. And then I go right into Ohm's law for I1 and I2, kind of like this, the problem we just solved. All right. So I1 is VG minus V1, which is V1 is 6, VG minus 6 divided by 2000. And I2 is V2, which is 6. I2 is V1 minus V3. So V1, which is 6 minus V3 divided by 4000. Okay, so I'm going to put those two things here, use them here, and then solve for V3. So I'm getting V3 here in terms of VG from that solution right there, right? So again, go back here. I put these two things in the KCL equations, and I can find a relationship between V3 and VG when I do that. So we get that, and then from V3, I can get V naught because V naught is essentially V3 minus 6 volt. Okay, so V naught is 12 volt minus 2 VG. Okay, so that's what I'm going to graph essentially that I was asked to graph. So if I do that, I graph from 0 to 12, and you can see it inverts. So V naught goes from 12 when VG is 0 to 12. I'm sorry, to minus 12 when VG is 12. Straight line down, basically. Okay. So that's the kind of problem that we're going to have a short quiz on op amp, but it's that level of complexity, not much. Though I'm going to do one more problem to show you a 2 op amp problem, but the analysis follow the same things that we're going to be doing here. Okay. So, and I hope that makes sense. All right. So this is a problem that asks you to find V naught. I wanted to show you this particular nomenclature because you will see that in technical journal and in obviously some textbook. So what you see is essentially, at first look, you might think there is 3 reference node. No, there's only 1 reference node in the circuit. All essentially this amplifies that these points are the same, they're connected to the same point. So this is the same electrical point, the reference node here that you see here. Okay, so you will see that a lot, and I wanted you to get some familiarity so that when you see a problem like that in a technical journal, it doesn't look so odd to you. So obviously, this is a problem that has 2 ideal op amps, and it's asking you to simply find V naught. All right, we're going to apply the same discussion points in terms of how do we treat the ideal op amps. So what I'm going to do, I'm going to put X, so no KCL here. no KCL here. So no KCL at the output of any ideal op amps, okay? We're going to say that these two terminals are the same value. That's one of the ideal op amp rules. These two terminals here are the same, have the same value, okay? And then we're going to essentially say zero current on the op amp terminals, input terminals. So zero current going in here, okay? And when I mean zero current, going in like this. Okay, so zero current going into the input of the op amps, okay? Because it has a lot. So these are the rules that we're applying on top of nodal. Obviously, you can see my reference node is already selected, so that basically is calling for nodal, and then we're going to solve it regularly. So let's put some node voltages here. So you can see me kind of doing V1 and V1 prime, because I want to make sure that I note them differently. I don't want to put V1 and V1 here because I want to talk about KCL at V1 and KCL at V1 prime. So I want to differentiate V1 from V1 prime. But one of the first thing I do is recognize that V1 equal V1 prime. Similarly for VA and VA prime, that's one of, the next thing I'm going to say. The input of the two inputs of the second op amp are also at the same value. So VA equal VA prime, but I want to name them differently. Okay, so I just want to make sure that you see that. And then you see me moving the 10 volt to that node. That's my source equation. Okay, the 10 volt moving into that node because the voltage source is connected to ground on the negative terminal. Okay, so I'm going to put current. I'm going to put current on my resistors. So I changed the picture a little bit so I can have room to work here because I had no room here given that circuit is so big. So I am essentially going to do KCL at node V1, at V1 prime, and at VA prime. No KCL at V0. Again, no KCL at VA because they're the output of an ideal op amp. So the only nodes that are left beside the super node and a reference node is V1, V1 prime, and VA prime. So this is KCL at node V1. I have I1 is equal to I4 plus I5, KCL right here. KCL at node V1 prime, again, remember that the op amp on the input terminal draws no current. KCL at V1 prime, we get I2 equal I3. And KCL at VA prime, we get I7 plus I6 equal to 0. So these are the three KCL equations for this circuit here. Of course, this circuit looks fairly complex, but it's fairly easy to solve. So, I just wanted to give you that look so that you get familiar to how sometimes we have reference node that we draw in multiple ways, but that doesn't mean different points. They're all connected electrically, okay? So I'm going to go ahead here and write Ohm's law for all of these currents. So I1 is 10 volt minus V1 divided by pi. So here you can see now that I've written the KCL, I've replaced V1 prime by V1 because I've already written the KCL, and I replace VA prime by VA. All right. So then you can see I1 is 10 minus V1 divided by 5,000. I2 is 10 minus V1 divided by 6,000. I3 is V1 divided by 12,000. And then I4 is V1 minus VA divided by 10,000. Okay. I'm going to do the same thing for I5, I6, and I7. Here they are. So I5 is V1 minus V0 divided by 20,000. I6 is VA. Where's I6? VA minus V0 divided by 2,000. And then I7 is VA over 20,000. I take all of these 7 currents, bring them to the 3 KCL equations, and then basically we're going to have 3 equations for 3 unknown, and we solve for V0, just like we do in nodal. So we have our 3 equations, 3 unknown, and what I want is V0. I don't necessarily need VA, V1. So I solve for V0, usually on my calculator or on the computer. And in this case, V0 is 2.36. So I'm hoping this gives you at least an introduction now to solve circuit with ideal op amp. Okay, we're not seeking for you to have an expertise. We're seeking for you to have some familiarity so that when you walk into an engineering technical, whether it's a technical a job that you're looking for, or at some point you're an engineer in a non-electrical engineering profession, that you have some introduction to op amps, what they do, and how to treat them at least on the ideal model. So I hope that served that. That in your homework, we will have a short quiz on that just to make sure you can do that. But the quiz will be in light of what you're just seeing here. 1 or 2 ideal op amps and asking you to solve for some voltages just to get you familiar with the concept and the practice. Thank you.